In Module 3, I will introduce you to the work energy theorem, and then we will look at conservative forces and non-conservative forces, and we will also briefly just look at the conservation of mechanical energy. You know that the kinetic energy of an object is the energy that the object has due to its motion. So if we have an object with a mass of m, and an initial velocity of vi, and there's a net force acting on this mass, then you know that that object will have a displacement of delta x and a final velocity of vf. So you know how to calculate the acceleration of this block, because in grade 10 you have done motion equations, and in grade 11 you have done Newton's second law. So if we use one of the motion equations, we can calculate the acceleration because we have the final velocity, the initial velocity, and the displacement, and then the acceleration, by just rearranging this formula, will be half vf squared minus half vi squared divided by the displacement. But in grade 12, you have learned how to calculate the net work done onto this object. The net work is equal to the net force applied to the object multiplied by the displacement of the object multiplied by the cos of the angle between the net force and the displacement of the object. And in grade 11 you learned that the net force is equal to the mass times the acceleration. That's Newton's second law. So we have that the net work done onto this object is the mass times the acceleration times by its displacement times by the cos of 0 degrees, because the net force and the displacement are both in the same direction. And if we substitute the acceleration with our rearrangement of the motion equation, we get that the net work is equal to the mass times half vf squared minus half vi squared divided by the displacement multiplied by the displacement. So the displacement above and below the line can cancel out, and we're left with half mvf squared minus half mvi squared. And this looks familiar, because the kinetic energy is equal to half mv squared. So if we have a final velocity and an initial velocity, it means that we have the final kinetic energy of the object minus the initial kinetic energy of the object. And that is just the change in kinetic energy of this object. So we end up with the net work done onto this object will be equal to the change in the kinetic energy of this object. Don't worry too much about the substitutions and manipulations that we've done here. What you have to know is the work energy theorem, and the work energy theorem states that when a net force acts on an object, the net work on the object is equal to the change in kinetic energy of that object. And the formula that you will use in your calculations is this one. The net work on an object is equal to the change in kinetic energy of that object. Let's apply this theorem to an example. A man pushes a wooden cart in an easterly direction by applying a horizontal force of 50 Newton to the cart. The weight of the wooden cart is 35 kilogram. Calculate the velocity reached by the wooden cart after the man pushed the cart from rest over a distance of 20 meters. The road exerts a friction force of 24 Newton on the cart. When they ask you to calculate the velocity, you have to think about kinetic energy. And the work energy theorem states that the net work done onto this cart will be equal to the change in kinetic energy of this cart. Now we can calculate the net work by using the net force and multiply that by the displacement of the cart multiplied by the cos of the angle between the net force and the displacement. And that will be equal to the change in kinetic energy. So it's the final kinetic energy minus the initial kinetic energy. so we need the net force. There's an applied force of 50 Newton, and then there is friction against the motion of 24 Newton. So the net force will be 50 plus the negative 24 of the friction. Multiply that by the displacement. They said it's over a distance of 20 meters. Multiply by the cos of the angle, and the angle here is 0 degrees because the net force and the displacement are both in the same direction. And that's equal to the final kinetic energy, which is half mvf squared, minus the initial kinetic energy, which is half mvi squared. Now, if you calculate the left-hand side on your calculator, it's 520. And on the right-hand side, we can substitute the mass. We know that the mass of the cart was 35 kilograms. We don't know what the final velocity is. We want to calculate the final velocity, but we do know that the initial kinetic energy was 0 because the cart was pushed from rest. So the initial velocity was 0, and therefore the initial kinetic energy will also be 0. And then you can calculate the final velocity. 520 divided by half of 35, and the square root of that answer will give you a final velocity of 5,45. We round off to 2 decimals, meters per second in an eastern direction. They asked you for the velocity, so you have to write down what the direction of this cart was. During a sports day, a boy pushes a plastic container with a mass of 50 kg from rest over a horizontal lawn with a constant force of 120 Newton. There is kinetic frictional force of 40 Newton on the plastic container, while the 120 Newton force is applied horizontally on the plastic container. Calculate the net work done on the container. So to calculate the net work done, we need the net force, and we know that there's an applied force of 120 Newton and kinetic friction of 40 Newton. So the net work will be equal to the net force multiplied by the displacement multiplied by the cos of the angle. And the net force here will be 120 plus a negative 40 because the friction is against the motion, multiplied by the displacement that was given to us on the diagram of 8 meter, and that multiplied by the cos of 0 degrees because the net force and the displacement are both in the same direction. And that gives us net work done of 640 joule. Now calculate the speed of the container at the end of the displacement of 8 meters. So if they ask you for the speed or velocity, and you know that you just calculated the net work, you have to think about the work energy theorem. So the net work is equal to the change in kinetic energy, that's the final kinetic energy minus the initial kinetic energy. You know that the net work is equal to 640. The mass of this container is 50 kilogram. We want to calculate the final velocity or speed, and you know that it was pushed from rest, so the initial velocity or the initial kinetic energy will be equal to 0. And then we calculate the final velocity. So it's 640 divided by half of 50, and the square root of that will give you 5,06 meters per second. No direction needed because they asked you for the speed, which is a scalar quantity. A wooden block with a mass of 2 kg slides from rest from position A on a frictionless surface as shown in the diagram. When the block reaches the bottom of the incline, it moves on a horizontal rough surface that exerts friction on the block of 10 Newton. Calculate the magnitude of the velocity of the block when it reaches position B. From A to B, there's no friction, so you can use the conservation of mechanical energy to calculate the magnitude of the velocity of this block at B. But I want to demonstrate the use of the work energy theorem. So the forces involved while this block slides from A to B are gravity and the normal force. So the only force doing work will be gravity. We have a displacement of 2 meters in the direction of the net force, which is gravity. So the work energy theorem states that the net work done is equal to the change in kinetic energy of this block. So the net work is the net force, which is just gravity, multiplied by the displacement of this block times by the cos of the angle. And that's equal to the final kinetic energy minus the initial kinetic energy. So the net force is just gravity, which is 2 times 9.8. The displacement is 2 meters in the direction of the net force, multiplied by the cos of 0 degrees, because the angle between the net force and the displacement is 0 degrees. And that's equal to the final kinetic energy, and we want to use that to calculate the final velocity, minus the initial kinetic energy, which is 0 because it slides from rest. And then we just calculate the final velocity. The final velocity is then 6.26 meters per second. No direction because they asked us for the magnitude of the velocity. Now calculate the magnitude of the velocity of the block when it reaches position C. So for a block moving on a horizontal surface, the only force that will do work is friction. The normal force and gravity are both perpendicular to the displacement of this block, and it won't do any work. So the net work done here is the work done by the net force, and that is only friction. So the friction is 10 Newton multiplied by the displacement, which is 3 meters from B to C, multiplied by the cos of 180 degrees, because the frictional force and the displacement are not in the same direction, they are opposite directions. And that's equal to half times the mass of 2, the final velocity, we want to calculate the final velocity, minus the initial kinetic energy, which is not 0 now because we know that the block had a velocity of 6.26 meters per second at B. And then to calculate the final velocity, it's 3.03 meters per second. No direction because they asked for the magnitude of the velocity. Calculate what distance after point C the block will come to rest. So the same forces apply, only friction force will do work, and we know what the initial velocity of this block at C is, and we know that it should come to rest. So the net work is done by the net force, in this case only friction of 10 Newton. We want to calculate the displacement or the distance. The angle between the displacement and the net force is 180 degrees. The final kinetic energy must be 0 because the final velocity must be 0. And then the initial kinetic energy will be the kinetic energy at position C, where the velocity is 3.03 meters per second. Then calculate delta x, which will be our distance in this case, is 0.92 meters. When we calculate the work done by a single force, in this case gravity, we use the work formula, and the force in this formula will be the weight of the object. The displacement is the height of the object, and the angle between the force and the displacement will be 0 degrees. So we get that the work done by gravity is equal to mgh. When this object has a displacement of delta x to the side, gravity will do no work because the force of gravity is perpendicular to the displacement of this object. But when this block is lifted to its original height, the work done by gravity will be minus mgh, because the angle between gravity and the displacement of this object is then 180 degrees, which gives us that negative sign. And sideways back to the starting point, gravity will do no work again because gravity is perpendicular to the displacement of this block. So the total work done by gravity to get this object from the starting position all the way around back to its starting position will be mgh plus 0 minus mgh plus 0, and that gives us a total work done by gravity for this movement of 0 joule. So it really doesn't matter what the original starting height of this block is, and it really doesn't matter what the sideways displacement of this block is. When the block returns to the starting position, the total work done by gravity is equal to 0. So the block can take any path, but when it gets back to the starting position, the work done by gravity will be 0. And that means the work done by gravity does not depend on the path taken by this block. Which brings us to the definition of conservative forces. A force is considered a conservative force if the work done by a force to move an object between 2 points is independent of the path taken. And you have seen that an example of a conservative force is gravity. So let's calculate the total work done by a non-conservative force, in this case friction. So for this example, let's take the same block as before, but we move this block against a wall so that there's friction between the wall and this block. Then the work done by friction will be equal to the frictional force multiplied by the distance or the displacement of the movement of this block against the wall multiplied by the cos of 180 degrees, because we know that the friction will be in the opposite direction to the displacement of this block. And that gives us a work done by friction of negative FH. Now, to keep this illustration simple, let's say that we keep this block against the wall while we push it to the right, and that there's no friction between the floor and this block. Then the work done by the friction against the wall will be the frictional force multiplied by the displacement to the right multiplied by the cos of 180, because the displacement and the frictional force will be in opposite directions again. So the work done by friction now will be negative Fx. So when we push this block back to its original height, the work done by friction will be again negative Fh, because the angle between the frictional force and the displacement of this block will be 180 degrees again. So when we push this block back to its starting position against the wall, the work done by friction will again be negative Fx. So the total work done by friction in our example where we move this block against the wall will be negative Fh plus a negative Fx plus another negative Fh and another negative Fx. So the total work done by friction will depend here on the h displacement, but also on the x displacement of this block against the wall. So the definition of a non-conservative force. A force is a non-conservative force if the work done by the force to move an object between 2 points depends on the path taken. And a very useful formula that we use with non-conservative forces is the work done by non-conservative forces will be equal to the change in kinetic energy of the object plus the change in the potential energy of that object. So examples of non-conservative forces will be forces like frictional forces or applied forces. A bucky with a mass of 900 kg is traveling at a constant speed of 36 km an hour at an incline with a constant slope. The distance uphill is 20 meters as shown in the diagram. The work done by the frictional force is 50 kJ and the work done by the engine is 72.3 kJ to get the bucky uphill. Use energy principles to calculate the height of the hill. In most of these examples, there will be more than one way to get to the answer. Study the different methods, practice them, and decide which one of the methods you are most comfortable with. When you answer a question in the question paper, start with the method that you're most comfortable with, and if it doesn't work, try any of the other methods. Because there's friction involved, we know that we will either use the work energy theorem or we will use the work done by the non-conservative forces. So we will start by looking at this example. Now the non-conservative forces here are the frictional force and the applied force of the engine. There's also gravity, but gravity is a conservative force, so we won't include that in the work done by the non-conservative forces. Now the work done by friction is 50 kilojoules, so it's 50,000 joule, and work done by friction will be negative. The work done by the engine is 72.3 kilojoules, so it's 72,300 joule. The change in kinetic energy is equal to 0 because this bucky is moving at a constant speed. And then the change in the potential energy will be the mass of the bucky times by gravitational acceleration times by the change in the height. So the height in this case is 2.53 meters. A second possible solution is where you use the work energy theorem. Now when you calculate the net work, you have to include all the conservative but also the non-conservative forces. That means you will have to include the work done by gravity. The change in kinetic energy is 0 because the bucky is moving at a constant speed. The work done by friction is negative 50,000. The work done by the engine is 72,300. And then we can calculate the work done by gravity. It's the weight, which is 900 times 9.8, multiplied by the height of the hill, multiplied by the cos of 180 degrees, because gravity is pulling downwards while the displacement of the bucky is upward. And that is equal to the change in kinetic energy, which is equal to 0. So if you calculate the height, then the height is 2.53. Now calculate the magnitude of the force applied by the engine. We know what the work done by the engine is, so if we want to calculate the force applied by the engine, we need to know what the displacement of the bucky is in the direction of this force applied by the engine, and then we will substitute 0 degrees. So the work done by the engine is 72,300. We want to calculate the force applied by the engine. We know that the displacement of the bucky in the direction that the force of the engine is applied is 20 meters, and then we can substitute 0 degrees for the angle, and that gives us a force applied by the engine of 3,615 Newton. You don't have to include a direction for the force because they asked for the magnitude of the force. In the first module, we said that mechanical energy is the sum of the gravitational potential energy and the kinetic energy of the object. Now, the law of conservation of mechanical energy states that in an isolated system, the total mechanical energy remains constant. Now, isolated system means that no energy is added or taken from this system. So, for example, there's no friction that does negative work to take energy away from the system. And this means that the mechanical energy at any position A will be equal to the mechanical energy of that same object at any other position B. So let's apply this to an example. A man with a mass of 80 kg jumps with a bungee cord around his ankles from the Orlando cooling towers in Soweto. The towers are 100 meters high. He falls 50 meters before the cord starts to tighten around his ankles. He falls another 40 meters before coming to a stop. Ignore all friction during the first 50 meters and use energy principles to calculate the kinetic energy of the man after falling 50 meters. If they ask you to use energy principles, they don't want you to use projectile motion or motion equations. So if they say you can ignore all friction, you know that the mechanical energy of this man at position A will be equal to the mechanical energy of this man at position B. And mechanical energy is the sum of the gravitational potential energy and the kinetic energy of this man. Now, the gravitational potential energy of this man is the mass of 80 times by gravitational acceleration multiplied by the height above ground level, which is 100, plus the initial kinetic energy at A, which is 0, and that must be equal to the potential energy at B. And this is where the mass is 80, gravitational acceleration is 9.8, but the new height above ground level is now 50 meters. Plus then the kinetic energy, and that's what they asked us to calculate. So the kinetic energy at position B is 39,200 joule. If you prefer to use the work energy theorem, then the work is done by gravity. The only force acting on this object while he falls for the first 50 meters is gravity. So the work done is the gravity force multiplied by the displacement of this man from A to B multiplied by the cos of 0 degrees, because the gravity and displacement are both in the same direction. And that will be equal to the change in kinetic energy. So the kinetic energy at B minus the kinetic energy at A. The weight of this man is 80 kilograms times by 9.8, and that multiplied by the displacement of 50 meters from A to B multiplied by the cos of 0, which is 1, of course. And that will be equal to the kinetic energy at B minus the initial kinetic energy of 0 at position A. And the answer then of the kinetic energy at B is 39,200 joule. Calculate the work done by the cord to put the man to rest. Now, we know in real life that if you have a bungee cord around your ankles, you will move up again. But they didn't mention that, and for our purposes here, we have to accept now that the man was put to rest at position C. So it stops at C. Therefore, in this case, the work done by the cord can only be the work done by a non-conservative force. So the work done by non-conservative forces will be the change in kinetic energy plus the change in gravitational potential energy. So if we expand this formula, then the work done by the cord will be equal to the change in kinetic energy, final minus initial kinetic energy, plus the change in potential energy, final minus initial potential energy. We know that the kinetic energy must be 0 at position C because this man comes to rest. And then the initial kinetic energy is the value that we calculated in the previous example, so it's 39,200 plus then the change in gravitational potential energy. So at position C there's a height of 10 meters, and at position B there's a height of 50 meters above ground level. And that gives us work done by the cord of negative 70,560 joule. Negative work because this cord must stop the man at position C. A second possible solution will be to use the work-energy theorem, and in this case probably a more suitable solution, because then we don't have to argue if the chord was a conservative or a non-conservative force. For the net work, we include all the forces, so it's the work done by the chord plus the work done by gravity, and that will be equal to the change in the kinetic energy of this man. So the work done by the chord is what we want to calculate. The work done by gravity will be the weight of the man, 80 times 9.8, multiplied by the displacement from B to C, which is 40 meters, and we will use the angle of 0 degrees because the weight and the displacement was both in the same direction. And that will be equal to the kinetic energy at position C minus the kinetic energy at position B. At C, it must come to a stop, so we know the kinetic energy will be 0, and the kinetic energy at B we calculated to be 39,200. So the work done, or the negative work done by this chord then, will be negative 70,560 joule. So we end off with this question: calculate the magnitude of the average force exerted on the man by the chord to bring the man to a standstill. We know the work that was done by the chord, and we know it was done over a displacement of 40 meters from B to C. So the work done by the chord will be equal to the force multiplied by the displacement multiplied by the cos of 180 degrees, because the chord was pulling up while the man was displaced downward. And that is the substitution, negative 70,560 joule, and that will be equal to the force multiplied by the displacement of 40 meters multiplied by the cos of 180, which is negative 1. And that gives us a force of 1,764 Newton. No direction, because they asked us for the magnitude of the force. If you are an educator that would like to inquire about the use of these PowerPoint slideshows in your classroom, you may contact me at lawsandwonders@gmail.com. Please indicate if this topic was useful to you or not, and subscribe to my YouTube channel in order to stay informed about the release of my most recent videos.